Welcome to the deep dive. Today, we're tackling a really massive topic. It's electronic waste, or e-waste.
Yeah, it's huge.
Globally, we're generating something like 20 to 50 million tons every single year. Just try to picture that. A mountain range of old tech.
It's staggering. And it's not just clutter, is it? It's packed with hazardous stuff, too. Heavy metals, plastics.
Right, things that can cause real problems if they just sit in a landfill or, worse, get burned improperly. Contamination risks.
Exactly. But what's really fascinating about e-waste, I think, is this dual nature. It's an environmental headache, sure, but it's also like this incredibly rich urban mine, seriously valuable resources locked away in there.
Okay, tell me more about that urban mine.
Well, think about the metals. Gold content can be around, say, 0.1%, silver maybe 0.2%, copper a whopping 20% sometimes, tin around 4%.
Okay.
Now get this. Typical gold ore, you're maybe getting 2 to 5 grams per ton of rock. So e-waste can be, 50, maybe even 100 times richer in gold than what we dig out of the ground. Imagine a truckload of old circuit boards versus a truckload of rock.
100 times richer. Okay. So we absolutely need to shift how we think about this. It's not just trash.
Not at all. It's a secondary raw material, a really valuable one.
So our mission today, then, is to kind of explore how we actually tap into this urban mine, the tech behind e-waste recycling, taking junk and turning it back into useful stuff.
That's the goal. And it fits into that bigger environmental picture, doesn't it? That sort of three-tiered approach.
You mean reduce, reuse, recycle?
Basically, yeah. First, try not to make so much waste. Then reuse things if you can. And for what's left, what can't be reused, that's where recycling comes in, finding environmentally sound ways to deal with it and recover value.
And it's not just about giving materials back, right? There are other benefits.
Oh, absolutely. Huge economic and energy-saving benefits. Recovering metals like aluminum, lead, copper, obviously the precious ones, gold, silver, platinum, and even critical metals like indium.
Indium, right, for screens and things.
Exactly. Producing these from recycled sources takes way less energy than primary production. Mining, smelting from ore, it's incredibly energy intensive.
So recycling saves energy, cuts down on mining impacts. Makes economic sense too, presumably.
Definitely. It's a win-win, really, if we can do it efficiently.
Okay, so how do we do it? If you've got this pile of old computers and phones, how do you get those valuable metals out? What are the main techniques?
Well, we're going to dive into 4 broad categories today. There's mechanical processing, sort of the physical breaking and solding part. Yeah. Then hydrometallurgical, which uses liquids, usually water-based solutions.
And water.
Pyrometallurgical, that's using high temperatures, think smelting.
Pyro.fire.
Right.
Okay.
And finally, electrometallurgical, using electricity.
Mechanical, hydro, pyro, electro. Okay, let's start with the mechanical. What's the main idea there?
Right. Mechanical pretreatment. The objective is basically liberation, freeing up the different bits, the metals, the plastics, the ceramics from each other.
Like taking apart a complex gadget into its basic components.
Kind of, yeah. But usually by breaking it down first, reducing the particle size, which increases the surface area, that makes the later separation steps much more effective.
How do you do that? Just smash it?
Well, smashing is part of it. The term is comminution size reduction. It involves different forces, pressure, so squeezing, impact, which is hitting, abrasion, rubbing things together, and cutting.
Okay.
You use different types of mills, hammer mills, knife mills, that essentially chop and pulverize the e-waste.
Any high-tech ways to smash things?
Actually, yes. There's something called cryogenic grinding.
Cryo. Like freezing.
Exactly. You use liquid nitrogen, super cold, to make the materials really brittle, especially the plastics and stuff. Then they shatter much more easily when you grind them.
Huh. Interesting. So how small do you need to grind things down?
Good question. It depends on the material, but for something like a printed circuit board, getting the particles down below, say, 2 millimeters, that often achieves almost complete liberation.
Liberation meaning the different materials are mostly separate particles.
Exactly. High liberation is key for the next separation steps. But there's a trade-off.
Always a trade-off.
The smaller you want to grind, the more energy it takes. It increases pretty dramatically. So you have to balance liberation degree with energy cost.
Makes sense. Okay, so we've ground everything down into small bits. What's next in the mechanical line?
Next is often size separation. Pretty much what it sounds like, sorting the particles by size.
Sieving.
Yeah, sieving is the most common method, using screens with different hole sizes. And interestingly, sometimes this step alone can help concentrate certain materials.
How so?
Because brittle materials like ceramics and ductile materials like copper break differently. So you might end up with, say, finer fractions being richer in one thing and coarser fractions in another.
Clever. Okay, sorted by size. What else can we sort by mechanically? Density. Heavy metals versus light plastics.
Absolutely. Density separation is crucial. It works because things with different densities settle at different rates in a fluid or get carried differently by air currents.
Right.
So you can separate the heavier metals, copper, iron, lead, nickel, from the lighter stuff like polymers, plastics, and light metals like aluminum.
But you needed that grinding step first, right? Especially for composite bits.
Oh, definitely. You need to liberate the components first before you can separate them based on their individual densities.
So what are the actual techniques for density separation?
There's quite a range. You've got air classifiers that just use airflow to blow away the light, fluffy, non-metallic stuff.
Simple enough.
Then there's dense medium separation. This is more precise. You use a liquid or a suspension that has a density between the densities of the materials you want to separate.
So the heavy stuff sinks and the light stuff floats.
Precisely. You might use salt solutions like calcium chloride or zinc chloride, carefully controlling the density. The viscosity, how thick the liquid is, also matters. You can do this in static tanks or in spinning cyclones for faster separation.
Okay. What else?
There are jigs. They use pulses of water flowing upwards through a bed of particles. The heavier particles sink faster between pulses. The lighter ones stay higher up. It stratifies the material by density.
Yeah.
And flowing film concentrators, think of things like shaking tables with little ridges or spiral concentrators. A thin film of water flows over a tilted surface, washing away lighter particles more easily than heavier ones.
Sounds like methods used in traditional mining, too.
Very similar principles, yes. Adapted for e-waste. And if water is an issue, you can use air separation or dry tables. Air flows up through a porous deck, fluidizing the particles, and then vibrations or tilting help separate them based on density and size.
Quite a toolkit just for density. What about magnets?
Yep, magnetic separation is another key tool, exploiting the magnetic properties, obviously.
Just pulling out the iron and steel.
Mostly, but it can be more sophisticated. Techniques like high-intensity magnetic separation, HIMS, and high-gradient magnetic separation, HGMS, use powerful magnets, electromagnets, sometimes even superconducting magnets, or strong, rare earth permanent magnets.
Yeah.
These can pull out not just ferrous metals, but also some weakly magnetic non-ferrous materials. By controlling the magnetic field strength, you can do selective separation. You have drum separators, belt separators, various designs for wet or dry processing.
All right. One more mechanical method you mentioned, electrostatic. How does electricity help sort things?
Right, electrostatic separation. This uses electric fields to separate particles that are either electrically charged or can be polarized.
How do you charge them up?
Several ways. Triboelectric separation uses friction. When different materials rub together, they can transfer charge just like static electricity.
Like rubbing a balloon on your hair.
Exactly that principle. Then there's counterseparation. You use a high-voltage electrode to create a field of ions. As particles pass through, conductive particles, like metals, pick up charge differently than non-conductive ones, like plastics. This is really common for separating metals from nonmetals in crushed PCBs, especially for finer particles.
Okay.
And then there's eddy current separation. This is mainly for non-ferrous metals like aluminum or copper. You use a rapidly changing magnetic field which induces electrical currents, eddy currents, inside the conductive particles.
Right.
These eddy currents create their own magnetic field that opposes the original field, effectively repelling the conductive particles away from the magnet. Great for kicking aluminum cans out of a waste stream, for example.
So it pushes the metal away rather than attracting it.
Exactly. And there are advancements like two-roll corona separators, making these electrostatic methods even more efficient.
Wow, okay. Mechanical processing is clearly way more involved than just smashing things up.
Yeah.
Now let's shift gears. Hydrometallurgical processing. Sounds like chemistry with water.
That's a good way to put it. Hydrometallurgical processing uses aqueous solutions, things dissolved in water like acids or bases, to selectively dissolve metals. It's chemical leaching.
Leaching, so you're washing the metals out.
Essentially, yeah. Dissolving them into the liquid phase. The key is selectivity, finding the right conditions and the right chemical leachant to dissolve the metal you want while leaving others behind as solids.
What factors affect how well this leaching works?
A few key things. Particle size. Again, smaller particles generally leach faster because there's more surface area for the liquid to attack.
Makes sense, like dissolving sugar cubes versus Granulated sugar.
Good analogy. Also, the type of solvent or leachant used, the temperature, how much you stir or agitate it, and the solid-liquid ratio, how much e-waste you put in a given amount of liquid. All these influence the speed and efficiency.
Are there different ways to do the actual leaching?
Yes. For large volumes of low-grade stuff, you might use heap leaching, basically piling up the material and letting the solution trickle through. More relevant for e-waste, though, are methods like vat leaching, or this really interesting one, bioleaching.
Bioleaching, using living things.
Exactly. Using microorganisms, certain types of bacteria, like Acetobacillus, or fungi, like Aspergillus or Penicillium species.
How on earth do microbes dissolve metals?
They have amazing biochemistry. Some bacteria work directly, attaching to the mineral surface and breaking it down. Others work indirectly. They produce oxidizing agents, like ferric iron ions, which then chemically attack and dissolve the metals.
That's incredible. What about the fungi?
Fungi often produce organic acids, citric acid, oxalic acid, things like that. These acids can act as leachants themselves, dissolving metal oxides. Plus, they can act as chelating agents.
Cholly.
Means they grab onto the dissolved metal ions and hold them tightly in solution, preventing them from just precipitating back out. It helps keep the metals dissolved.
Nature's little chemists doing recycling. Amazing. Any other hydro techniques? You mentioned supercritical fluids. Sounds like sci-fi.
It's pretty advanced, yeah. Supercritical fluid extraction, you use a fluid that's heated and pressurized above its critical point.
What happens then?
In that supercritical state, it has properties of both a liquid and a gas. It can dissolve things like a liquid but penetrate solids easily like a gas.
What kind of fluid?
Carbon dioxide, CO2, is really common. Its critical point isn't too extreme, it's cheap, non-toxic, and environmentally pretty benign. When you release the pressure, it just turns back into a gas, leaving behind whatever it extracted.
So you use it like a solvent?
Exactly. You can tune its dissolving power by tweaking the temperature and pressure. Sometimes you add a little bit of another solvent, like methanol, a co-solvent, to help dissolve specific types of compounds. It's used to extract solids from solid materials.
Very cool. Okay, so hydro methods get the metals dissolved into a liquid. How do you get them out of the liquid and purified?
That often involves solvent extraction, which is also called liquid extraction.
Liquid.
Yeah, you take your aqueous solution containing the dissolved metals and you mix it with another liquid, usually an organic solvent that doesn't mix with water, like oil and water.
Okay.
This organic solvent contains a special chemical called an extractant. The extractant is designed to selectively grab onto specific metal ions and pull them out of the water phase into the organic phase.
Ah, so you move the desired metal from the water to the oil, so to speak.
Pretty much. Then you let the two liquids separate, and you drain off the organic phase, which now holds your target metal. You can then strip the metal back out of the organic phase into a clean aqueous solution, often by changing the acidity.
And you can do this multiple times to get purer metals.
Yes, it can be done in batches or continuously, often in multiple stages working countercurrently for high efficiency and purity. There are different types of extractants: acidic, basic, neutral, chosen for their selectivity, capacity, stability, and cost. It's a really powerful technique for separating, say, cobalt from nickel, or separating rare earth elements from each other.
Okay, that covers hydro. Next up, electrometallurgical processing. Using electricity, you said.
Right. The main process here relevant to e-waste recycling is electrowinning.
Electrowinning. It sounds like you're winning metals with electricity.
That's basically it. You take the solution containing the dissolved metal ions, often the solution you got from hydrometallurgical leaching, and you pass an electric current through it using electrodes.
An anode and a cathode.
Exactly. The positive metal ions in the solution are attracted to the negatively charged cathode. When they reach it, they gain electrons and deposit onto the cathode as pure solid metal.
So you essentially plate the metal out of the solution.
Precisely. Meanwhile, at the anode, something else has to get oxidized. Often, it's water molecules being split into oxygen gas and hydrogen ions.
Any downsides?
Well, that anode reaction producing acid can sometimes create acid mist, which isn't great. Also, there's a limit to how fast you can plate the metal out, the limiting current density. If you try to go too fast, push too much current, the quality of the metal deposit can suffer, becoming powdery or rough instead of a smooth layer.
So it's mainly used after leaching to get things like copper or precious metals back in solid form.
Yes, it's very common for copper recovery and often used in the final stages of precious metal refining after leaching.
Got it. Okay, final category, pyrometallurgical processing. the high temperature route.
Yep, pyro means fire. Here, we're using heat, often very high temperatures, to melt, oxidize, and separate the components of e-waste.
Like smelting in traditional metal production.
Very similar. The equipment is often adapted from primary metallurgy, things like isosmelt or Caldo converters, electric arc furnaces.
So what happens when you throw, say, circuit boards into one of these furnaces?
The shredded e-waste is heated up, often with coke as a fuel and reductant, and oxygen or enriched air. We're talking maybe 1,200 degrees Celsius, sometimes higher.
Wow. What happens to the different materials?
The plastics and organic materials basically pyrolyze, break down due to heat and combust, actually providing some energy back into the process, which is neat. Impurities, like some base metals and the oxides from glass and ceramics, get oxidized and form a molten slag layer, kind of like a glassy waste.
And the valuable metals.
The valuable metals melt and collect together, often dissolving into a molten metal phase. Copper is often used or produced as a collector metal because precious metals like gold, silver, and platinum dissolve really well in molten copper.
So you end up with a layer of molten copper containing the precious metals and a layer of slag on top.
That's the basic idea. The slag contains the ceramic and glass components, but unfortunately it can also trap some valuable metals, so you can get some losses there.
And then you have to process the copper phase further.
Exactly. That metal phase, rich in precious metals, then needs further refining, usually using hydrometallurgical and electrometallurgical steps to separate and purify the individual metals like gold, silver, platinum, palladium.
Are there big companies doing this?
Oh, yes. Companies like Umicore in Belgium have a highly integrated smelter and refinery specifically designed for complex e-waste. Noranda in Canada also has processes adapted for this. It's a major route, especially for complex mixes like PCBs.
Okay, that covers the 4 main processing routes. Now maybe we can zoom in on recycling some specific components. Printed circuit boards, PCBs seem like a big one.
Definitely. PCBs are kind of the heart of most electronics, and they're incredibly complex little things.
What are they actually made of?
It's roughly 40% metals, 30% polymers or plastics, and 30% refractory oxides, basically ceramics and glass fibers.
And the metals aren't just copper.
Oh, no. Lots of copper, yes, but also significant amounts of precious metals, gold, silver, palladium, plus iron, tin, nickel, lead, aluminum, and sometimes smaller amounts of critical or hazardous metals like tantalum, indium, gallium, arsenic, cadmium, mercury. It's a real cocktail.
Which explains the environmental concerns if they're just dumped or burned improperly, right? Releasing lead, cadmium, mercury.
Heavy dioxins from the waste. Exactly. That's why we have regulations like RoHS, restriction of hazardous substances, trying to limit those harmful materials in the first place, and We E-Waste electrical and electronic equipment directives pushing for proper collection and recycling.
So how do you tackle recycling something that complex?
Usually involves a combination of techniques we've discussed.
Right.
You almost always start with mechanical, pretreatment shredding, grinding, size separation.
To liberate the components?
Right. Then you apply physical separation methods. Gravity separation, maybe dense medium separation if the particles are large enough, generally works better above about 0.6 millimeters. Magnetic separation, often in multiple stages with varying field strengths to get different metals. And electrostatic separation, both corona type for metal, non-metal separation and eddy current for recovering aluminum.
So you try to get concentrated streams of different materials mechanically first.
That's often the aim. After that, you might use hydrometallurgy, leaching out the base metals like copper, then perhaps leaching the precious metals. Or the mechanically processed material, or even whole PCBs, can go into a pyrometallurgical process, like a copper smelter.
Which route is better?
They both have pros and cons. Integrated smelters can achieve very high recovery rates, often over 95% for valuable metals. But a big challenge, especially with mechanical hydro routes, is dealing with that large non-metallic fraction, the plastics and fiberglass. They're often thermosetting resins, meaning they don't easily remelt like typical thermoplastics.
So what happens to that non-metal part?
Historically, and still quite often, it ends up in landfill. There's ongoing research into using it as filler material or finding other applications, but it remains a significant challenge.
What about monitors? We've all transitioned from those big, heavy CRT monitors to flat LCD screens. How has that changed recycling?
Big changes. Those old cathode ray tube CRTs were dominated by the glass tube itself, maybe 60% of the weight.
Right, they were heavy.
And that glass is tricky. The front panel glass used barium, but the back funnel glass and the neck contain a lot of lead for radiation shielding.
Lead. That's a major hazard.
Absolutely. If CRT glass ends up in landfill, that lead and barium can leach out. So recycling is crucial. There was closed-loop recycling where the glass was used to make new CRTs.
But we don't really make main CRTs anymore.
Exactly. So the focus shifted to open-loop recycling, using the glass for other things. But variations in the glass composition, especially that lead content, make it difficult to just melt down and use in, say, bottles.
So what do?
The monitors are dismantled glass separated from plastics, the circuit board, metal parts like the shadow mask, the electron gun. Then there are specific processes to chemically remove or stabilize the lead from the funnel glass. Some companies developed processes for this. There's also research into using the leaded glass, safely encapsulated in things like ceramics, tiles, or even concrete.
Trying to find a safe home for it. Okay, what about the LCDs, liquid crystal displays, that replace them?
They present a whole different set of challenges. They're much lighter, but structurally very complex.
What's inside an LCD screen?
You've got the front plastic cover, the frame, then the actual LCD panel, which itself is layers of glass substrates coated with transparent electrodes made of indium tin oxide, ITO.
ITO, there's the indium.
Yep. Between the glass layers, you have the liquid crystals themselves, plus polarizing films, diffuser sheets to spread the light. Then there's the backlight unit.
The light source.
Right. In older LCDs, this was often cold cathode fluorescent lamps, CCFLs, which contain mercury.
Mercury, another hazardous material.
Exactly. Newer ones use LEDs, which is better. Then you have the circuit board driving it all, and the back cover.
Sounds like a nightmare to recycle.
It is challenging. The concentration of any single valuable material, apart maybe from the indium, is quite low compared to a PCB, plus the mercury hazard in older ones. And recovering the liquid crystals themselves, not really commercially viable currently.
But the indium is important.
It's very important. Indium is considered a critical raw material essential for technology, but with potentially constrained supply. So recovering indium from those ITO layers is a major focus.
How is that done?
Usually involves acid dissolution to get the indium and tin off the glass, followed by separation techniques like precipitation or solvent extraction. A lot of indium actually gets recycled from the waste generated during making the ITO targets and screens in the first place. Most of this recycling happens in the countries that produce a lot of displays like China, Japan, and Korea.
Okay, one last category. Batteries. Especially with electric vehicles and all our portable gadgets, battery recycling must be huge.
It's becoming increasingly critical, yes. Let's think about two main types. Older nickel-cadmium, nice did, and the now dominant lithium-ion, L-libs.
NiCads is the ones with cadmium, right? Toxic.
Highly toxic. They contain nickel, cadmium, iron, plastic. Cadmium use is heavily regulated now because of its toxicity, so recycling these is essential to prevent environmental contamination. It typically involves physical separation followed by pyro or hydro methods to recover the nickel and cadmium.
And lithium-ion, they're everywhere now.
Absolutely. LIBs have various chemistries, but key components include the cathode, positive electrode materials, often lithium metal oxides like lithium cobalt oxide, or phosphates like LiFePU4. The anode, negative electrode, usually carbon-based materials like graphite, sometimes silicon or titanium oxides. And the electrolyte, which allows ions to move, can be liquid, polymer, or even solid state in newer designs.
What are the recycling challenges for LIBs?
The biggest one is safety. Lithium is highly reactive, especially with air or water. Damaged batteries can overheat, catch fire, or even explode.
Right, you hear about battery fires.
Plus, during mechanical processing like shredding, toxic or flammable gases can be released depending on the battery state and chemistry. So safety precautions are paramount.
So how are they recycled carefully?
It usually starts with discharging them safely, then dismantling or shredding, often under inert atmosphere or specialized conditions. Then, like other e-waste, it branches into pyrometallurgical routes, smelting to recover metals like cobalt, nickel, copper, while the lithium often ends up in the slag or flue dust or hydrometallurgical routes.
Leaching again.
Yes, using acids or sometimes alkaline solutions to dissolve the valuable cathode metals like cobalt, nickel, manganese, and lithium. Then techniques like precipitation and solvent extraction are used to separate and recover them. Recovering high-purity lithium efficiently is still a major area of research and development.
This has been incredibly illuminating. It's clear e-waste is this complex mix, a huge environmental challenge, definitely, but also this amazing reservoir of resources.
Absolutely. We've seen this whole toolbox of techniques: mechanical breaking and sorting, hydros chemical dissolution, pyros high heat melting, electros electricity-driven recovery, all being deployed.
To recap for everyone listening, it's just staggering that, your old phone could have gold concentrations way higher than what's mined from the earth.
That really sticks with you, doesn't it?
Yeah.
And the hidden complexity things like recycling an LCD screen, dealing with hazardous materials like lead, mercury, cadmium, or the very real safety issues in handling lithium-ion batteries.
Yeah.
But also the innovation, like finding ways to potentially upcycle old CRT glass into something new. It shows how much effort is going into tackling this.
And it really underscores the importance of proper e-waste management globally and how regulations can drive better recycling practices. We all have a role to play in how we dispose of our old tech.
Definitely. And maybe this leaves you with a final thought to chew on. What if we design electronics differently from the start?
How do you mean?
What if products were intentionally designed for easier disassembly, for simpler material recovery at the end of their life? Could we engineer things so that this whole recycling process becomes significantly easier, cheaper, and more efficient? And looking ahead, what completely new technologies might emerge in the next 10 years to revolutionize how we handle electronic waste?
Designing for recyclability
Right.
and future tech breakthroughs, that's definitely something to think about.